तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, the first order of business is to compute this number to find the inner product x with p. That is going to be a basic input. You recall that p ket vector stands for a momentum eigenstate of a particle moving on a line, x ket vector stands for a position eigenstate, and what we would like to find out is, given the commutation relation, given this, given the fact that x commutator p is IH cross times the unit operator, where these are operators, given this basic commutation relation, we would like to find out what is the overlap between a position eigenstate and a momentum eigenstate. So this is our task. We know already that when two operators do not commute with each other, you can't find a complete set of common eigenstates for these two operators, it is not possible. So the question is, given this commutator, this is the commutation relation, that is an input information borrowed from classical mechanics, from the Poisson bracket we went to the commutator, we would like to find out what this quantity is. But we already saw last time that the momentum operator in the position basis, this operator here, this matrix element is nothing but minus IH cross d over dx of the representative of the state psi in the position basis. So we established this relationship last time, that followed, that piece of information followed directly from this commutation relation. So all that is in the commutation relation has been put into this thing here. So it says in the position basis the momentum operator acts as if it is minus IH cross the derivative operator with respect to x. We will use that information to compute what this quantity itself is. Instead of psi, you replace it with the momentum eigenstate in this equation, and that is going to immediately tell us what the answer is. So we have x p on p equal to minus IH cross d over dx x with p. Okay. But of course the momentum operator acting on a momentum eigenstate just produces the momentum eigenvalue outside. So this p is a label, a number, call it p0 if you like. So this says minus IH cross d over dx of x with p is equal to p times x with p, because this is a number that comes out when this operator acts on it, it produces the eigenvalue, it comes right out of the inner matrix element and it is equal to this. So this function, this is some function of x labeled by p, that function, call it f of x if you like, that function satisfies an ordinary differential equation in the x variable, and the solution, this implies that x with p is proportional to, apart from some constant, it is proportional to e to the power, so this is just a constant, I bring the IH cross down here, so it is IP over H cross x, and that is true for every p. We could have changed the value of this p to some other eigenvalue, whatever be the eigenvalue, you get this equation here with that eigenvalue present and this x sitting here. Mind you, this is a function of x because it is a position space representative of a certain ket vector. That ket vector is labeled by this p here. So this gives us a fundamental result which says x with p, apart from some normalization constant, if you can normalize it, is essentially a phase factor. Notice that in that exponent there is no question of putting operators or anything like that, both x and p are numbers, actual numbers, they are eigenvalues actually. So corresponding to this ket bra here you have an eigenvalue x, that is number is sitting here, corresponding to this ket you have an eigenvalue p, that is sitting here. And of course this immediately implies that p with x is proportional to e to the minus ip x over h cross. Now the labels x and p interchange in this case. This is the p representative, p space representative of a position eigenstate x, and it is just this quantity here. We already proved, remember, that if you took a state vector psi of t and you asked what is its position space representative, this was equal to psi of x comma t, and similarly in the momentum basis equal to psi tilde of p and t, and this psi tilde of p and t was related, this guy here was related to, you could put a dp and then an x p p psi of t. I insert a complete set of states there, and this is equal to, this is the unit operator when I sum over p, this is equal to integral dp, but x with p is e to the I p x over h cross, and this quantity is psi tilde of pi p and t. So it says that psi of xt is a Fourier transform of psi tilde of p and t and vice versa, and you can fix the constants by adjusting, by making sure, by having a Fourier transform normalization convention. So this quantity here is equal to that, and of course psi tilde of p and t is dx e to the minus I p x over h cross psi of x with t. Okay. So that establishes my assertion made earlier that the position space and momentum space wave functions of a particle, quantum mechanical particle, are Fourier transforms of each other. That immediately tells us that if one of them is square integrable, so is the other square integrable, because you know by the Parseval's theorem mod psi squared of x comma t integrated over the x is equal to the same thing for p, mod psi tilde. So that is just a conservation of probability statement, and both of them belong to L2. This incidentally is also one way of looking at it, of the statement that the space L2 is self-dual. So the Fourier transform of a square integrable function is also square integrable. Okay. So much for the representative, so this overlap x comma p. One can generalize this to 3 dimensions. So if you have in 3 dimensions the momentum eigenstate p labeled by the momentum vector p, and you ask what is its position space representative, this is proportional to e to the power I, obviously p dot r over h cross in 3 dimensions, and similarly the other guy is e to the minus I p dot r. Okay. And in that case the momentum, the representative, this relation here becomes r p operator acting on psi is equal to minus I h cross the gradient operator acting on r psi. This gradient is with respect to r, the label r. Okay. So we have this very important statement that in L2 minus infinity infinity the representation of the momentum operator is in fact minus I h cross the gradient operator. Okay. So that is the basic reason why differential operators appear so naturally in quantum mechanics, because automatically starting with the original canonical commutation relation between a coordinate and its conjugate momentum, the derivative operator appears naturally. Okay. So this is why the Schrodinger equation, for instance, turns out to be a differential equation and so on. In fact, we can now write it down. We can write down the Schrodinger equation for a particle moving in space. So let us do this in 3 dimensions. The Schrodinger equation for a particle. We are now talking about non-relativistic physics. So the Hamiltonian of this particle is p squared over 2m, plus it could be in some potential which is a function of the coordinates alone. Quantum mechanically these are operators, so I should really write h of r p. I should put little caps over these guys to show that they are operators, but by now we have become used to this notation, so it is obvious by context that these are operators, so we will not clutter up the notation. The Schrodinger equation is IH cross d over dt psi of t equal to the Hamiltonian operator acting on psi of t. That is the abstract equation. The question is, what does it look like in the position basis? And to do that, all you have to do is to take the position basis, some particular labeled position eigenstate R, and take scalar products on both sides with respect to this guy. So out here I put R H psi of t. I want you to note particularly the fact that this psi of t, this abstract state vector, that is not burdened by things labels like R, P and so on and so forth. That is just the state of the system. It is a vector in some Hilbert space. The variables that describe the system, the physical system, are in this case R and P, and you talk about eigenstates of those variables. But this is some abstract state, it does not have any labels except it changes with time, that is it. But now what is this equal to? Well, I can pull this d over dt outside and then it acts on this guy alone, but then the representative R with psi of t is what I call the wave function. So I could pull this out and write IH cross d over dt R with psi of t, but this is the wave function of the particle in the position basis, and I have got a name for this. So this is equal to psi of R and t, just the wave function in the position basis. But now this looks like a function of two variables, and I must be careful to note that the time derivative acts on the explicit time dependence here. Therefore this should really be written IH cross delta over delta t to make it completely unambiguous that this t derivative is going to act on that t dependence which came from the t dependence of the state vector, and this is equal to, on this side you have an R and then you have a p squared which is an operator over 2m acting on psi of t here, plus an R, a v of R, and then a psi of t once again. We can now simplify both these terms, we are in a position to simplify both of them. P operator, the matrix element of P in the position basis is minus IH cross the gradient acting on R on psi, right. Therefore P squared is minus IH cross gradient dot minus IH cross gradient, because P squared is just P dot P. So that tells us that the first term on the right hand side, so it says IH cross delta over delta t psi of R comma t equal to minus IH cross squared minus IH cross squared del squared, because del dot del is del squared when acting on scalars, over 2m psi of r comma t plus a certain quantity here. What should I do with this? I do not know what r operator, this is an operator and this is some function of r operator, I do not know what function it is, depends on the potential. I do not know what it does when it acts on psi, but I know what r operator acting on r bra vector does, it just pulls out the real eigenvalue r, this label here. Therefore any function is also, this is an eigenstate of a function of r as well, and it pulls out just the corresponding function of r that v of r is. Suppose this v of r is r squared plus e to the minus r as an operator, then it acts on this bra vector, it pulls out r squared plus e to the minus r as an eigenvalue. Therefore we could write this as v of r, and now this is an ordinary function multiplying bra r with psi, which is psi of r and t. Pardon me? It should be what? It is acting on a bra, so it should really be v star, it should be v star of r star. We should be careful in doing this, but now I am talking about a Hermitian Hamiltonian because I would like its eigenvalues to be real, it is a physical quantity. Therefore this function v I have assumed is real, good point, I have assumed the function v to be real. If it is complex, then we should have to interpret what the imaginary part means. There are problems where this works, there is a need for complex potential. When you have a beam of particles impinging on a quantum mechanical target, quantum particles, part of it would be scattered, part of it would be absorbed, and then one uses a complex V in order to take into account absorption, because then probabilities need not be conserved, the Hamiltonian need not be Hermitian. So it is necessary to take into account those situations, but right now I have in mind a particle in a real potential here. So this then is the position space wave function for a particle, and this is what you would have seen in the hydrogen atom problem. This is precisely what you have seen in the hydrogen atom problem, where V of r is the Coulomb potential that an electron sees in a hydrogen atom, it is minus some constant over r. Of course some simplification occurs in this partial differential equation when you have spherical symmetry. If V of r is spherically symmetric and depends only on the distance little r without a vector sign, then it is convenient to take this del squared and write it out in spherical polar coordinates and solve the problem by separation of variables by assuming that this wave function psi of r vector comma t is a product of functions of r, theta and phi, and then the matter separates out completely. So you can see that the solution of this kind of equation would depend, it is a complicated equation, it is not a trivial equation even for a single particle, it is first order in time, it is second order in the space variables here. So it is a complicated partial differential equation, you need to specify initial values, boundary conditions and so on and so forth. What boundary condition would you specify for a physical particle moving in 3-dimensional space? You would say the total probability of the existence of the particle is 1. Therefore you would normalize your psi of t by saying that at all instants of time this probability amplitude shall remain equal to 1, but that written out on the position basis is nothing but d3r psi of rt whole square. By d3r I mean the volume element in real space. And that is true for all time. That condition is called the normalization condition. It implies therefore that this wave function psi of r comma t, the position space wave function, is a member of L2, but L2 with 3 independent variables x, y and z or r, theta, phi, whatever. So this here is an element of some L2 space. It follows that this can only be true if, as the distance, radial distance goes to infinity, mod psi goes to 0. That is a necessary but not sufficient condition. It should go to 0 sufficiently fast that this number remains finite and bounded. Now you can ask, what sort of problems can I solve with this? Well, by separation of variables you can solve all those problems where this partial differential equation splits into equations for each of the independent variables. The separation into time is not very hard, we will see in a minute how to do that, but the separation of the space variables depends on the form of V of r. It is not very clear what would happen in general. What is the equation for a free particle? No V of r at all. Then you can't normalize it because a free particle can move all the way from minus infinity to infinity, and if it is in a momentum eigenstate it goes like e to the I p dot r whose mod is 1 and therefore cannot be normalized. Then you would pretend that you would put it inside a box of some size L and let L go to infinity. This is called box normalization. We will come back to this when we do the particle in a box problem. Okay. But you could also ask, in what coordinate systems does del squared separate in 3 dimensions? That is a problem purely in calculus, and it turns out there are 11 different orthogonal coordinate systems: Cartesian, spherical polar, cylindrical polar coordinates, oblate spheroidal, prolate spheroidal, parabolic cylinder, elliptic coordinates, and so on. There are 11 different coordinate systems in which the del squared operator separates, okay. And there is a mathematical condition on what is called the stable determinant which specifies this, but this is not of too great interest because unless the potential has that kind of symmetry you will not choose that particular given coordinate system. All spherically symmetric potentials, spherical polar coordinates is what you would choose. If it has got Cartesian symmetry you would choose Cartesian coordinates, and so on. We will solve a few such problems, but this equation is what I would like you to examine and appreciate and ask, what do we do next? Well, the first thing one could do is actually get rid of the time dependence. And what does that imply? That brings us to the idea of eigenstates of the Hamiltonian itself, stationary states. A stationary state of a quantum mechanical system by definition is an eigenstate of the total Hamiltonian of the system. Any stationary state is an eigenstate of the Hamiltonian of the system. In general, the Hamiltonian operator may have a very large number of eigenstates, in general an infinite number of eigenstates. Any one of them is called a stationary state. So eigenstates of H itself. Okay. What does that imply? It says IH cross d over dt psi of t must be equal to h psi of t for any state. But if it is an eigenstate of the Hamiltonian, then h on psi reproduces the same state. So let me use a special notation for it. Let us use phi for an eigenstate of the Hamiltonian for the moment. So this is equal to phi of t, but this is equal to eigenvalue times phi of t, some number. Since I know at the back of my mind that the Hamiltonian classically in conservative systems really represents the total energy of the system, the value of the Hamiltonian gives you the total energy. I borrow that language and go over to quantum mechanics and I say the eigenvalue of the Hamiltonian, let me call it E, capital E. As yet we do not know whether this E is continuous, whether it is discrete, positive, negative, we do not care. We do know it is real, and the reason is I insist that the Hamiltonian be made up of observables and therefore its eigenvalues are guaranteed to be real for the systems we are looking at. So skip this line and use this fact here. So this guy is the eigenvalue, an eigenvalue, and it is real, and phi of t is the corresponding eigenstate. Of course there is no guarantee that phi of t is unique for a given E. There may be more than one such eigenstate. After all, when you diagonalize matrices, you know that an eigenvalue may be repeated, in which case you have two or more eigenvectors for the same eigenvalue. If you have finite dimensional matrices, the eigenvalues are all discrete. N by n matrix can at best have n distinct eigenvalues, but that is not true when you have other more complicated operators. In general, the eigenvalue spectrum could be partly discrete, partly continuous, and so on, could be fairly complicated. But let us say this is an eigenvalue to start with, it is a number, all we know is that it is a real number. Then it immediately follows that phi of t is e to the minus I e t over h cross phi of 0. It immediately follows, in other words, the Schrodinger equation is solved trivially for an eigenstate of the Hamiltonian. Moreover, the time dependence of the Hamiltonian of the state vector is just the initial state multiplied by a phase factor, a factor with modulus equal to 1, whereas that is not true in general. It is certainly true when you have an eigenstate of the Hamiltonian that the time dependence of the state is utterly trivial. And in fact, apart from a phase factor, and any factor of the form e to the I theta is called a phase factor, modulus 1 complex number is called a phase factor. Apart from a phase factor, the initial state persists. So if you have a system, quantum system, in an eigenstate of its Hamiltonian, it remains so, apart from a phase factor, which is unimportant really in some sense, because it does not do anything, it does not change the normalization. Phi of t remains equal to phi of 0 here. A single exponent oscillating with a frequency which is equal to E over h cross. That is it. That is not true in general, and the reason it is not true in general is because we can use this now to ask what happens in general. Can I use this to write down the Schrodinger equation solution in general? Well, for a general state, psi of t, we could do the following. We could write psi of t equal to a summation over the eigenstates of the Hamiltonian, and let us pretend for a minute that the eigenstates are labeled by some quantum number n. You may ask now, why should it be one quantum number, why should it be a positive integer or anything like that, just a set of quantum numbers. Let me use the index n for it, and we will see later on that this n could be a continuous variable, it could be more than one number, but symbolically if it is written in this form Cn phi n, where these are eigenstates of the Hamiltonian, then it is easy to see that I have two ways of looking at this. One of them is to say I will choose as my basis set phi n of 0 at t equal to 0, in which case the time dependence of this gets thrown into Cn of t. The other way of doing it is to say no, I choose my coefficients once and for all, in which case the time dependence gets thrown into this. But these are equivalent because phi n of t is e to the minus I e t e n t over h cross phi of 0. So let us put ourselves out of our misery by writing this expansion. It does not matter how I write this, psi of t equal to summation over n C n e to the power minus I e n t over h cross phi n of 0. I will frequently use this without the 0 here, but without any time argument, and by that you must understand that I have chosen a basis set once and for all which is time independent. Yeah. How do I know it is a basis? There is a theorem which tells me that if I choose an appropriate set of mutually commuting observables pertaining to a system, then these are all Hermitian alpha joint operators, when the common set of eigenstates is can be made orthonormal, is linearly independent and spans the space. In other words, it forms a basis. Okay. I should check in suspicious cases, I should check whether really I have covered everything, whether things span the space or not, but right now take it as an assertion that the Hamiltonian in general will provide such a basis set. You could ask what happens about degeneracy. Take again the hydrogen atom problem. There the basis set is provided by the stationary states of the system, which are labeled by 3 quantum numbers n, l and m. The energy happens to depend only on n, but really in the more general case it would depend on n, l and m as well. So I have used a single symbol to take into account all possible quantum numbers. In general there will be more than one quantum number. In general there will be as many quantum numbers as there are degrees of freedom in the system, and for a particle moving in space there are 3 degrees of freedom. That is why in general in potential problems in 3 dimensions there would be at least 3 quantum numbers. There may be more if there are internal quantum numbers in the system like spin or hypercharge or strangeness and so on and so forth for elementary particles, but at least 3 quantum numbers. Sometimes in books you would notice a thing like this written down, S n, to show it is a summation over n, integration when it is continuous and summation when it is discrete and so on, but we will just use the notation sigma n in this case. These coefficients are the overlap at t equal to 0 of phi n with psi, and they are time independent, they are fixed. Now what is different about this as opposed to this in the time dependence? There is a superposition here, there is a superposition of states here, there is a single state here and it is multiplied by a time varying, time oscillating phase factor. Here you have time oscillating phase factors, but they are different phase factors for different states. Notice carefully that as the state changed I even changed the energy eigenvalue to show that that is different for different states. So what is different about this as opposed to that? What new phenomenon would have happened here that does not happen there? If you have a single sine, this is by the way e to the I et is a sine and cosine, so think of it in terms of sines and cosines. You got sine, a single frequency, that is just a sinusoidal wave, but you add more and more frequencies, sinusoidal waves with different frequencies, and then what happens? You could have interference, you could have beats, you could have groups formed, you could have modulation. So all the effects that you could have when you superpose more than one frequency would start appearing here. In fact in general if this spectrum is infinite, goes up to infinity, then all kinds of wild possibilities happen. These different frequencies are in general not multiples of each other, they are not commensurate with each other. So when you add up different time frequencies which are not even commensurate with each other, you could have even aperiodic functions. The function could become aperiodic if it goes right up to infinity. It is not a Fourier series, because that would happen if this En was just n, then you have cos nt and sin nt, but these are E sub n's, there are some complicated functions of n, they may have n squared, n cubed, all sorts of dependencies, so it can become horrendously complicated. In fact all quantum interference phenomena happen because of this superposition implied here.
Those eigenstates are orthogonal, right?
I have assumed that these are orthogonal to each other, orthonormal, pardon me?
Then how can there be superposition?
Why not? Why not? X and y coordinates are orthogonal to each other. A general vector in 2 dimensions is a superposition of something along x and something along y. They are orthogonal to each other, that is the whole point, so that the coefficients will uniquely determine this vector. If they were not orthogonal, that is not true, then you have oblique coordinates. So I have assumed these have been orthogonalized by the Gram-Schmidt procedure, and then there is a superposition, and the time dependence is exceedingly complicated, need not even be periodic. It could be almost periodic, it could be quasi periodic, it could be very complicated in general. So you need not even have periodicity, it could be highly irregular functions. So it is not a Fourier series at all. This is very, in principle it is written down very easily, but in practice this is a very intricate function here. So this thing here leads to quantum this superposition, this summation here leads to quantum interference effects. Can we see what happens in the position basis in a similar situation? Well, all we have to do is to plug this whole thing into this thing here and write this as equal to E psi of r and t, because I know IH cross psi of r and t is E psi of r and t, and you have to solve this equation here. Now what does this imply? What does IH cross d psi over dt delta over delta t psi equal to E psi imply? This immediately implies that psi of r comma t is proportional to e to the power minus I e t over h cross. Only then if you differentiate with respect to t do you end up with this quantity here. What is the quote unquote constant of proportionality? What can that depend on? It can depend on r, the other variable r, so I should not call it a constant, I should immediately say this is equal to a function of r times this guy here. What notation shall I use for that function of r? What is the value of that function? It is the value of psi of r comma t at t equal to 0, because if I put t equal to 0 the exponent goes to 1. So without any loss of generality I could really write this as psi of r comma 0. Now of course I have abused notation a little bit, so I should say for a stationary state, I should say that. So let us be careful. For a stationary state, then I promised that I would use actually phi for that variable for the state vector. So let us use little phi for this wave function to be consistent with our notation, phi of r comma t, that is phi of r comma 0, it says phi of r t is equal to this. So this guy here is phi of r comma 0, and without much loss of generality in notation let me just call this equal to e to the minus I e t over h cross phi of r, without putting the 0 for the t, I just call it function of r. Okay. That is for one stationary state, but for the general stationary state which is labeled by this quantum number n, then of course I have n here, and then this is n here, this is n here, and this is E n here and phi n, and it says phi n is E n t phi n E n phi n. Okay. Again with this caveat that this little n which is labeling the eigenstates of the Hamiltonian may actually be more than one label, could be a set of quantum numbers. So this is what a given position space wave function would do for a stationary state. And of course this expansion that I have written down here, if I now work in the position basis and I do an r here that goes right across and hits this guy here, so this becomes phi n of r. And what is Cn? What is the Cn equal to? What is the coefficient equal to? It was the overlap in the position basis between r and the state of the system at t equal to 0. So it says the general state at time t in the position basis, the wave function is just given by this superposition. And the crucial thing here is to find out what the hell are these functions, what are these functions, how do I solve that? Well, that I solve by putting it back in here. I use that fact that this was equal to that, which is h psi equal to IH d by dt psi, but I use the fact that this phi is a stationary state by saying h psi equal to E psi, and I solve this portion of it, and the solution looks like that for each of these eigenstates. Now I put that back in this portion out here, and what does it say? It says minus h cross squared over 2m del squared phi n of r times e to the minus I e t e n t by h cross plus v of r phi n of r e to the minus I e n t by h cross is equal to E n times phi e to the minus I e n t by h cross phi n of r. That is what the Schrodinger equation becomes for a stationary state. But there is no derivative with respect to t. I have removed it, I have in fact solved the t dependence here, and this factor of course cancels out. That is exactly what happens when you separate variables, it just goes away, this factor disappears, this factor disappears, and I am left with this equation. For each eigenstate, the position space representative of that eigenstate satisfies this partial differential equation. It is still a partial differential equation, but at least you got rid of the t. And of course you work in one dimension, it is an ordinary differential equation. If you work in one space dimension, this thing here is called the time independent Schrodinger equation. What is the difference between the time dependent Schrodinger equation and the time independent Schrodinger equation as a differential equation? Of course one of them has t and the other does not have t, that is a different story, but as a differential equation, as an operator equation, what is the difference? You have to appreciate this right away, because then it means you have understood what is going on. This is a general equation. What is the difference? There is a very big difference between this equation and this equation. Yeah, this has a first order term, that is gone, this has time dependence, that is gone here, but there is a fundamental difference between this equation and this equation. What sort of equation is this? Pardon me? Pardon me? Okay, technically yes, it is elliptic and so on and so forth, but other than that, even more basic than that, as an operator equation, the second one is an eigenvalue equation. This is an eigenvalue equation, absolutely right. This guy here says take this differential operator del squared plus v of r act on phi n of r and you are guaranteed to get a number, real number times phi n of r, this thing here. This is an eigenvalue equation. It is a homogeneous equation, so is the other one, because you multiply phi by a constant it does not change, but most important it is an eigenvalue equation. And of course you solve this subject to boundary conditions now, there is no initial no time here, so subject to boundary conditions, impose those, impose normalization if you like, and then out come the eigenvalues. Now what we are going to do is to take this equation now, this is the time independent Schrodinger equation, the eigenvalue equation, and the statement is If you give me a general state of the system no matter what it is and you tell me the initial state, I will tell you the future state by actually computing these eigenfunctions, substituting in this equation here, and then this is a constant which you tell me at t equal to 0, and that gives me the solution at any time. So that is the strategy. You have to find the eigenvalues of the Hamiltonian, and after that the general time dependence of the state is obvious and the general behavior of the state is obvious. It is just a superposition of these eigenfunctions with suitable phase factors here. Okay. So is this clear? This is the way you would solve in principle the Schrodinger equation. So you exploit the fact that the Hamiltonian plays a very special role. It is the generator of time translations for the system. So it is not surprising that the time dependence of its eigenstates is particularly simple, and that is used to put in the time dependence of a general state out there. But the price you pay is you have to solve an eigenvalue equation, and now it turns out that very interesting things happen when you have an eigenvalue equation, because this you are familiar with vibrations of a string clamped at both ends. You have a wave operator, you have a second derivative operator, its eigenvalues and eigenfunctions would depend not only on the operator but also on the boundary conditions. So the boundary conditions would determine if you have a string which is tied at both ends, clamped at both ends, or left one end loose the other end free, the normal modes change completely. That is what is going to happen here. So not only is this differential operator important, but its boundary conditions are also important in determining the spectrum. We will see in a minute that if you put a particle in a box, the energy levels get quantized immediately, as opposed to a free particle which could have any energy from 0 to infinity. As soon as you put it inside a box, even if it is free inside the box, the boundary conditions will ensure that only a certain set of energies is allowed by boundary conditions. So that is going to emerge as a consequence here. That takes me to an interesting sidelight. You know that the hydrogen atom, so let me make this general statement rather loosely, any confinement of a quantum system tends to quantize something, any restriction tends to quantize something. So you put a particle in a box, it quantizes the energy levels. You put it in a potential which is a confining potential, again the energy levels get quantized under suitable conditions. You take angular momentum, and you know angular momentum is quantized in units of Planck's constant, and the reason is the corresponding dynamical variables, the angles, really do not run from minus infinity to infinity. They really run from 0 to 2 pi for the azimuthal angle and 0 to pi for the polar angle. That is enough to produce quantization. So confinement sort of produces quantization under suitable conditions. We will see how this comes about in a very precise way. So when Schrodinger first solved the wave equation and he wanted to reproduce the hydrogen atom spectrum, he solved this wave equation, and a very brilliant piece of work, but he was not sure how he was going to produce a discrete spectrum, because you put a hydrogen atom, you put an electron in the Coulomb potential of proton, then there is no box, there is no confinement, this particle can run, the potential extends all the way to infinity. So where is the confinement, where is the condition? And then he consulted David Hilbert at Göttingen, the greatest mathematician of the time, and Hilbert pointed out to him that the requirement of square integrability of the wave function, which was needed for total probability equal to 1, that is sufficient to say for that you need that the wave function must vanish at spatial infinity, and the requirement of square integrability, meaning that the wave function must belong to L2, that acts as confinement. That boundary condition is enough to make the spectrum discrete. Okay. In the hydrogen atom that was certainly the case. So even a condition like without a physical box, just the fact that the whole wave function mod squared must be finite when you integrate, that is sufficient to produce a discrete spectrum. So in most potential problems that is what the requirement of square integrability changes the spectrum. So an important lesson in eigenvalue equations, the eigenvalue is determined not just by the operator for differential operators but also by the boundary conditions that specifies the class of solutions that are admissible. very often. So the spectrum itself is determined by the operator plus the boundary conditions always. So let us take that problem and simplify it enormously to do our one dimensional particle in a box problem. We will complete this tomorrow, but let me set it up now, then we stop. So sometimes it is called a free particle in a 1D box, but I will point out to you that it is not as free as all that. So now I have the x axis, and on the x axis from 0 up to L on the x axis I have a box and there is a particle, quantum particle put inside it. The outside of the box is not accessible to the particle, not accessible. You stuck the particle inside the box, and I assume that the walls of the box are perfect reflectors, no absorption at the ends, it is not sticky, it does not absorb, it does not do anything. Classically this is a very simple problem to solve. So let us do this completely classically, figure out what happens and then come back to the quantum problem, write down the Schrodinger equation and solve it, because a great deal of quantum mechanics, a fairly surprisingly large part of quantum phenomena can actually be understood by this trivialist of problems. Many things can be understood. So let me use this as a kind of exercise which we can do very easily, trivially, in order to explain all these phenomena one by one. The first thing we have to ask is, what is the Hamiltonian of the particle? Classically the Hamiltonian of the particle is just p squared over 2m, just the kinetic energy plus a potential. So let us write that potential, it is a function of x alone. What kind of potential is it? It is 0 inside the box, and I do not want the particle outside, so it is infinite outside, rigid walls, infinite. So this V of x what does the phase diagram look like? Here is x, here is p. This particle can only exist between 0 and L, so this is a forbidden region and that is a forbidden region, and then depending on what you do inside, what the initial conditions are, the particle will start moving. So classically if you start at some point here and it is moving with a velocity, with a momentum p, let us say, it goes up here, it slams against the wall, momentum reverses, comes back here and keeps doing this. So it is quite clear that this is going to just be straight line trajectories. So if it starts here, it goes up there, it hits the wall, it reverses momentum, comes back here, hits this wall, jumps up, reverses and keeps following this trajectory. And you have to specify for me the number p, which is equivalent to specifying the total energy. So this guy here, this intercept is square root of 2me, and this intercept is minus square root of 2me. That is the phase trajectory. It is discontinuous at the two ends because this particle instantaneously reverses momentum. There is nothing more, that is it. For any initial condition, for any p, it is just going to go back and forth in this fashion. Let us do old Bohr-Sommerfeld quantization, then I stop. The old rule said integral for a periodic orbit p dx was equal to Planck's constant times an integer. That is Bohr quantization, the Bohr quantization rule. This was postulated by Niels Bohr. Of course after the Schrodinger equation came in, this got thrown out, but it is actually back. This is the semi-classical result, and I will come back and explain why this is a very profound result. It is a highly non-trivial result, highly non-trivial way of looking at it, and it is a very crucial input in quantum mechanics. So suppose we apply that to this problem here blindly. What is integral p dx over a closed period? It is the area of this thing here, and that area is the area of the rectangle, that is twice square root of 2me, this length, multiplied by the length there, that is L times L. This must be equal to NH, and that must be true for n equal to 1, 2, 3 etc. So let us label the n's, E is by writing E sub n, and this immediately implies that En equal to n squared h squared over 8 m l squared. So it immediately predicts quantization of the energy. It says these are the only allowed values for the energy. What we have to see is whether the exact Schrodinger equation, which we are going to solve imposing correct boundary conditions, reproduces that, and in this case this was believed to be true only for sufficiently large n, but it will turn out here that in this case this is in fact true as an exact result. If you solve the Schrodinger equation, this is exactly what you get, and we will try to understand why, because there is a deep reason why this is true. So that will be our starting point. Tomorrow we will start with the Schrodinger equation, that equation, the time independent equation in one dimension for this simple potential problem, and try to solve this. Meanwhile, think a little bit about whether the energy eigenstates are also position eigenstates or not for this particle.